Hi, welcome to this Corbettmaths video. In this video, we're going to look at the video solutions to the Corbettmaths Practice Questions on the volume of a frustum. If you need any extra help on the volume of a frustum, if you go to Corbettmaths and go to the videos and worksheet section and scroll down to video number 360A, there's a dedicated video tutorial there on finding the volume of a frustum. But in this video, we're going to focus on the video solutions to the practice questions, so let's get started. Okay, so question number one. Question number one says, shown is a square-based pyramid A. So we've got this square-based pyramid, and the base of it is a square. As you can see, it's 24 centimeters by 24 centimeters, and the perpendicular height of the pyramid is 30 centimeters. And in part A, we've been asked to find the volume of this pyramid A. So to find the volume of a pyramid, we do a third the area of the base times the height. So the volume is equal to a third the area of the base times the height. So if we find the area of the base by doing 24 times 24, that'll give us the area of the square, so that'll be the A. And then the height is 30, that's the perpendicular height. And then we can just find the volume by doing a third the area of the base times the height. So let's do that. So the volume is equal to a third multiplied by the area of the base. Now it's a square, so we're going to do 24 multiplied by 24, and that's equal to 576. So the area of the base is 576 centimeters squared. So the A is going to be 576. And then multiplied by the height, the perpendicular height, that's going to be 30. So if we do a third multiplied by 576 multiplied by 30, that'll give us the volume of that pyramid. So let's do that. And that's equal to 5,760 centimeters cubed. So that's the volume of that pyramid, 5,760 centimeters cubed. And then if we go down here, we've got some more information here. We've got shown as a smaller square-based pyramid B. So this is a smaller square-based pyramid, and we've been asked to find the volume of this pyramid. So to find the volume of this pyramid, again, we're going to do the volume is equal to a third the area of the base times the height. So it's a square-based pyramid, so let's get the area by doing 4 multiplied by 4, and 4 times 4 is 16, so the area of the base is 16 centimeters squared. So that means the volume of that pyramid, the volume would be a third, multiplied by A, the area of the base, that's going to be 16, multiplied by the height, the perpendicular height of that pyramid is 5. So if we do a third, multiplied by 16, multiplied by 5, that'll be the volume of that square-based pyramid B. So let's do that. And that's equal to 26.666 and so on. So 26.6 recurring centimeters cubed. So that's the volume of that square-based pyramid B. So 26.666 and so on. And that's fantastic. So we've done part A and part B. Now let's carry on the question. Okay, so if we carry on with the question, we're then told a frustum is created by removing pyramid B from the top of pyramid A. So if we have that pyramid A and we take away that pyramid B from the top of it, what's left is that frustum there. And we've been asked to find the volume of that frustum. So what's fantastic here is we've worked out the volume of the whole pyramid A. We've worked out the volume of pyramid B, that's been taken away. So if we subtract, that'll tell us the volume of that frustum. So if we do 5,760, subtract 26.666 and so on, that'll be the volume of that frustum. So let's work that out. And that's equal to 5,733.333 and so on centimeters cubed. And that's it, that's the volume of that frustum, 5,733.333 and so on centimeters cubed. And that's it. So just to recap on this question, we found the volume of that square-based pyramid by doing a third the area of the base times the height. We then found the volume of the smaller square-based pyramid, B, and then we took the volume of the smaller one away from the volume of the bigger one because that was removed, and what was left was the volume of the frustum. And that's it. Okay, let's take a question number 2. So question number 2, we've been shown a cone, so this is cone A, and the radius of the base of the cone is 12 centimeters, and the perpendicular height of the cone is 18 centimeters. And part A asks us to find the volume of this cone. So the volume of a cone, the volume is equal to a third pi r squared, h. So to find the volume of a cone, we do a third the area of the base, so pi r squared is the area of the circle, and then times the perpendicular height. So it's the same technique as finding the volume of a pyramid, where we do a third the area of the base times the height, but because it's a circle, it's going to be pi r squared. So we've been asked to find the volume of this cone, so we're going to do the volume is equal to a third multiplied by pi, multiplied by the radius of the base, which is 12 squared, multiplied by the height, which is 18. And if we work that out, we'll get the volume of that cone. So let's do that. And that's equal to 864 pi, or as a decimal number, 2,714.336,053 centimeters cubed. And let's just round that to 3 decimal places. So that's going to be 2,714.336 centimeters cubed. Okay, and then if we carry on, part B. Okay, so part B says, shown as a smaller cone B. So this is a smaller cone B. The radius of the base is 6 centimeters, and the height of the cone, the perpendicular height of the cone, is 9 centimeters. And we've been asked to find the volume of that cone. So the volume will be equal to a third multiplied by pi multiplied by the radius squared times the height. So that would be a third multiplied by the area of the circle, which would be pi times 6 squared, times the height of the cone, which is 9. And when we work that out, we'll get the volume of that cone. So let's do that. And that's equal to 108 pi, or as a decimal number, 339.292 and so on centimeters cubed. So that's 339.292 centimeters cubed to 3 decimal places. Okay, and then if we carry on, we're then told a frustum is created by removing cone B from the top of cone A. So this whole cone would be cone A. This cone that's been removed is cone B, and what's left is the frustum. So to find the volume of the frustum, we just need to take away the volume. So we need to do the volume of the larger one, which was 864 pi, subtract the volume of the smaller one, which is 108 pi. We could do it in terms of pi, or you could use the decimal numbers, 2,714.336,053, subtract the volume of the smaller one, which is 339.2920066. Now, one thing to note there is that whenever I'm doing the subtraction, I tend not to use the rounded version of the answers, and I tend to use the whole calculator display, or in terms of pi. And whenever we do that subtraction, we get an answer of, that's equal to 756 pi, or as a decimal number, that'll be equal to 2,375.044046. And let's just round that to 3 decimal places. That'll be 2,375.044 centimeters cubed. And that's it. Okay, let's look at our next question, question number 3. So question number 3 says a frustum is made by removing a small pyramid from a larger pyramid. So we've got this larger pyramid here, and then this smaller one that's been removed, and then what's left is the frustum. And we've been asked to find the volume of the frustum. There's a couple of approaches that we could use here. One approach is to consider similar shapes, or the second approach, which is going to be the approach that I'm going to use, is to work out the volume of the smaller pyramid, to work out the volume of the larger pyramid, and to subtract the volume of the smaller one from the volume of the larger one, and what's left would be the volume of the frustum. So let's do that. So let's consider the larger pyramid to begin with. The larger pyramid is a square-based pyramid. It's 12 centimeters by 12 centimeters in terms of the base, and the height of the larger pyramid is 15 centimeters. So let's find the volume of that larger pyramid to begin with. So the volume would be equal to a third the area of the base A times the height H. So that would be equal to a third multiplied by the area of the base. Well, it's 12 times 12, that's 144 centimeters squared. So times 144 times the height of that pyramid, which is 15. And then if we work that out, that'll be the volume of the larger pyramid. So if we do a third times 144 times 15, that's equal to 720 centimeters cubed. So that's the volume of the larger pyramid. I'm just going to write that down, larger pyramid. Okay, now in terms of the smaller pyramid, the volume will be still a third the area of the base times the height. The area of the base will be 8 times 8, which is 64 centimeters squared. The height is 10, so that means the volume will be a third multiplied by 64 multiplied by 10. And when we do that, we get an answer of 213.333 and so on centimeters cubed. Okay, so that's fantastic. We now know the volume of the whole pyramid. We know the volume of the pyramid that's been removed. So when we subtract them, then what's going to be left will be the volume of the frustum. So let's do that. 720 subtract 213.333 and so on is equal to 506.6 recurring centimeters cubed. So that's 506.666 and so on centimeters cubed. And that's it. So let's write that down on the answer line, 506.666 and so on centimeters cubed. Okay, let's have a look at our next question, question number 4. So question number 4 says, shown below is the frustum of a pyramid that had a perpendicular height of 40 centimeters. So there was a pyramid that had a height of 40 centimeters, and this is the frustum that's left after the pyramid at the top's been removed. The top of the pyramid has been chopped off. And then we've been asked to find the volume of that frustum. So if I want to find the volume of this frustum, what I would do is I'd consider the whole pyramid. So I'm just going to do a little sketch here. So it's not going to be the best, but this is just a quick sketch. So this is the whole pyramid going up like so. And the whole pyramid had a height of 40 centimeters. So if the height of the whole pyramid is 40 centimeters and the height of the frustum is 24 centimeters, this part here must have a height of 16 centimeters because 40 take away 24 is 16. So we know that this pyramid has been removed from the top of the bigger pyramid, and what's left is the frustum that we want to find the volume of. So what I'm going to do is I'm going to find the volume of the whole pyramid. So I'm going to do the volume is equal to a third the area of the base times the height. I'll do that to find the volume of the whole pyramid, and then I'll do the same for the smaller pyramid that's been removed, and then take them away, and then what's left will be the volume of the frustum. So let's start off with the big pyramid, so the larger pyramid, the large pyramid. So the large pyramid, we're going to do the volume is equal to a third. The area of the base, now it's not a square base pyramid, it's a rectangular base pyramid. So we're going to do 30 times 25 to get the area of the base of the pyramid. So 30 times 25 is equal to 750 centimeters squared, so 750 centimeters squared. That's the area of the base of the whole big pyramid. So the area of the base is 750 times the perpendicular height of the whole pyramid, which was 40. So then if we work this out, this will tell us the volume of this whole pyramid. So let's do that. 750 times 40 times a third is equal to 10,000. So 10,000 centimeters cubed. That's the volume of the whole pyramid. Now what I'm going to do is I'm going to work out the volume of this smaller pyramid, and then we'll take that away from 10,000. So for the smaller pyramid, let's go down a little bit. The volume of that pyramid will be, the volume will be a third, the area of the base times the height. So we're going to do a third. The area of the base. So let's have a look at the smaller pyramid that's been removed. So in terms of this pyramid, it's a rectangular based pyramid. It's got a length of 12 centimeters. The base has got a length of 12 and a width of 10. So it's a rectangular base. So we're going to times them together to get the area of the base. And 12 times 10 is 120. So 120 centimeters squared. So we're going to do a third times the area of the base, which is 120, multiplied by the perpendicular height of that smaller pyramid is 16. So times 16. And when we do that, we'll get the volume of that pyramid. So let's do that. 120 times 16 times a third is equal to 640. So 640 centimeters cubed. So that's the volume of the pyramid that's been removed. So if we take them away, what's left will be the volume of the frustum. So let's do that. And when we do 10,000 take away 640, that's equal to 9,360 centimeters cubed. So that's the volume, 9,360. And that's it. Okay, let's look at our next question, question number 5. So question number 5 says, shown is the frustum of a cone that had a perpendicular height of 12 centimeters. So here's the frustum, and so there was an original cone. I'm just going to do a little sketch there. And the original cone had a height of 12 centimeters. Now, cone's not necessarily the best. The lines obviously should be straight going up there, so perhaps there would be a better point to go to. In terms of the height of the original cone, the height of the frustum is 9 centimeters. The height of the original cone was 12 centimeters. So that means that the extra bit here, this extra bit here, would be 3 centimeters. So that's fantastic. We've now got a sketch of the original cone, and we know that this cone on the top has been removed, and we've been asked to find the volume of this frustum, this part here. So let's find the volume of the large cone, and then find the volume of the smaller cone, and take them away to find what the volume of the frustum would be. So let's write that down, large cone. So for the large cone, the volume is equal to a third pi r squared h. A third, the area of the base times the perpendicular height. So for the large cone, that'll be a third times pi times the radius of the base for the large cone is 8 and then squared, multiplied by the perpendicular height, which would be 12. And when we work that out, we'll find the volume of the large cone, and that is equal to 256 pi centimeters cubed, or as a decimal number, 804.2477193, and so on. Now, I personally like to use it in terms of pi because that's exact and I don't necessarily need to worry about rounding and things like that. So whenever I take away, I'm going to be taking it away from the 256 pi. Now let's find the volume of the smaller cone. So for the small cone, So for the small cone, again, the volume is going to be equal to a third multiplied by pi r squared h. The radius of the base of the small cone is 2 centimeters, so that's going to be a third multiplied by pi multiplied by 2 squared multiplied by the height of the small cone, which is 3, so multiplied by 3. And when we work that out, we'll find the volume of the small cone. So let's do that. So it's a third multiplied by pi multiplied by 2 squared times 3, and that's equal to 4 pi, so 4 pi centimeters cubed. So that's the volume of the small cone, or you can write it as a decimal number as 12.56637061. Now, we've been asked to find the volume of the frustum, so let's take them away. So the volume of the large cone is 256 pi, subtract the volume of the small cone, which is 4 pi, and let's work that out. Or you could do 804.2477 and so on, subtract 12.566 and so on, and then you'll get an answer of 252 pi. So 252 pi, or as a decimal number, 791.68 and so on. And that's it. Now I'm going to give my answer to 2 decimal places, so that's going to be 791.68 centimeters cubed. That's the volume of that frustum. 791.68 centimeters cubed to 2 decimal places. Okay, let's look at our next question, question number 6. So question number 6 says, shown below is a frustum of a cone. So we've got this frustum of a cone, and we've been asked to work out the volume of the frustum. Now this question is a little bit different than the ones we've been given so far, because so far all the questions have told us the original height of the cone or of the pyramid, but in this question we've just been given the height of the frustum. So what I'm going to do is I'm going to turn it back into the original cone, so I'm going to just carry this on like so. And then that will be our original cone, and we know that a smaller cone's been chopped off to leave us with the frustum. Now what would be really useful in this question is if we could work out the height of the original cone, if we could work out the whole height. Because if we knew the whole height of the original cone, we would then also know the height of this smaller cone, and then we'd be able to work out the volume of both of them and then take them away to find the volume of the frustum. So let's do that. Now what I'm going to do is I'm going to do a little sketch of the smaller cone and the larger cone. Okay, so I've just drawn sketches of the smaller cone and the larger cone. So we've got this smaller cone here, it's just viewed from the side, this smaller cone here. We know the radius of the base is 2 centimeters, and then we've got the larger cone, and the radius of the base of the larger cone is 12 centimeters. Now what I notice then is that the larger cone, the radius is 6 times bigger than the smaller one, because if we do 12 divided by 2, that's equal to 6. So it means that the larger cone is 6 times larger than the smaller cone. And these cones will be mathematically similar. The larger one will be an enlargement of the smaller one. So here, the scale factor of enlargement is 6. Now that's going to be really useful. Now that we know the scale factor of enlargement is 6, we can then use that information and also the fact that the height of the frustum is 20 to work out the height of the smaller cone and the larger cone. Okay, so let's look at the smaller cone. I'm going to call the height of the smaller cone h. So h. That stands for the perpendicular height of the smaller cone. Now for the larger cone, we know that the height of the larger cone is 6 times larger. So the height of the smaller cone is h. The height of the larger cone will be 6 times larger. So that's going to be 6h, because h times 6 is 6h. And that makes sense because if we look at the radii, the radius of the larger cone is 6 times larger than the radius of the smaller cone, and the height of the larger cone is 6 times larger than the height of the smaller cone. So that's fantastic. Now that's going to be quite useful because if we actually have a look at this, we know the height of the frustum is 20 centimeters. And the height of this part here, this smaller cone, we call that h. So this part here is h. The height of this smaller cone is h. So that means that we've got 2 expressions for the height of the larger cone. We know by considering here that the height of the larger cone is 6h, but also we've got the height of the larger cone from our diagram is h plus 20. So that's an equation. The 6h would be equal to h plus 20. So let's write that down. 6h is equal to h plus 20. So if the height of the smaller cone is h, the height of the larger cone would have to be 6h because it's 6 times larger. But also if the height of the smaller cone is h, that means the height of the whole cone here from our diagram would be h plus 20. So it means that 6h equals h plus 20. Now let's solve that equation. If we take away h from both sides of the equation, if we take away h and take away h, on the left hand side we'll be left with 5h, And on the right hand side, we had h plus 20. We're taking away the h, so we just be left with 20. So we've got that 5h equals 20. So that means that h would have to be equal to 4. So it means the height of the smaller cone is 4 centimeters, and the height of the larger cone is 6 times h. So 6 times 4 is equal to 24 centimeters. And if we just check that, if the height of the smaller cone is 4 centimeters, the height of the larger cone is 24 centimeters. So that's perfect. So that's fantastic. So we now know for the smaller cone, its radius of its base and its perpendicular height. And also for the larger cone, we know the radius of the base and the perpendicular height. So we can now work out the volume of both of those cones and take them away to find the volume of the frustum. So let's do that. Okay, so the volume of a cone is equal to 1/3 pi r squared h. And then if we consider the large cone, so for the large cone, we're going to do 1/3 multiplied by pi, multiplied by the radius of the base, which is 12 squared, multiplied by its perpendicular height, which we find to be 24. So when we work that out, that'll tell us the volume of the larger cone. So let's do that. And when we do that, we get an answer of 1,152 pi centimeters cubed. So that's the volume of the larger cone. You can do it as a decimal number, and that's 3,619.114737, but I'm just going to leave it in terms of pi at the minute. I'll do the same for the smaller cone, and then whenever I subtract them, then I'll change them into a decimal number. Okay, so for the smaller cone. Okay, so for the smaller cone, the volume is going to be 1/3 multiplied by pi, multiplied by the radius of the base, which is 2, and then squared, multiplied by its perpendicular height, which was 4. And when we work that out, we get an answer of 16/3 pi centimeters cubed. So that's fantastic. We now know the volume of the larger cone. We know the volume of the smaller cone. And we can now subtract them to find the volume of the frustum. So let's do that. And when we do 1,152 pi, take away 16/3 pi, we get an answer of, and I'm going to write it as a decimal number here, 3,602.359576 centimeters cubed. And I'm going to round that. I'm going to round it to 2 decimal places. So the answer to 2 decimal places would be 3,602.36 centimeters cubed. And that's it. Okay, let's look at our next question, question number 7. So question number 7 says, shown below is the frustum of a square-based pyramid. And we've been asked to work out the volume of the frustum. Okay, so let's have a look at this. So we've started off with a large square-based pyramid, and a smaller, similar small-based pyramid has been removed. So let's start off by looking at the larger square-based pyramid, and let's find the volume of that larger square-based pyramid. So the volume would be equal to 1/3 the area of the base. That's a square-based pyramid, so if we do 60 times 60, we'll get the area of the base. So it's going to be 3,600 centimeters squared. So the volume, it will be equal to 1/3 the area of the base times the perpendicular height, so that'll be 1/3 multiplied by 3,600 multiplied by the height, the perpendicular height of the larger square-based pyramid, which was 48. And when we do that, we'll get the volume of that square-based pyramid. So let's do that. And that's equal to 57,600 centimeters cubed. So that's the volume of the larger square-based pyramid. But a smaller one's been removed. So let's find the volume of that smaller square-based pyramid. So the volume, again, will be equal to 1/3 the area of the base, so that's going to be 20 times 20 is equal to 400 centimeters squared, so times by 400, times by the perpendicular height. So we need to find the perpendicular height of this smaller square-based pyramid. Now, if we have a look at them, we know they're mathematically similar, the smaller square-based pyramid and the larger square-based pyramid. And if we look at the side length of the squares, so the lengths of the base, so here and here, we can see that the larger one is 3 times larger. So that means the height of the larger square-based pyramid would be 3 times larger than the height of the smaller one. So if we divide by 3, if we do 48 divided by 3, that's equal to 16. So that means the height of this smaller square-based pyramid was 16 centimeters. So that means we're going to do 1/3 times the area of the base, which is 400, times the perpendicular height, which is 16. And when we do that, we'll get the volume of that smaller square-based pyramid that was removed. So let's do that. And that's equal to 2,133.333 and so on centimeters cubed. So that's fantastic. We now know the volume of the larger square-based pyramid, what we started with. We know the volume of the smaller one that was removed. So if we take them away, we'll find the volume of the frustum. So if we do 57,600 subtract 2,133.3 recurring, that's equal to 55,466.6 recurring. And that's it. So let's write that down. The volume of the frustum is 55,466.67 centimeters cubed to 2 decimal places. And that's it. Okay, let's have a look at our next question, question number 8. So question number 8 says, shown as the frustum of a pyramid. So here's the frustum of a pyramid. So the top of it's been chopped off. And it's a rectangular base pyramid, because as you can see here, the length of it is 7.5 centimeters and the width is only 6 centimeters. And in terms of the top of it, we know that this length is equal to 3 centimeters. We're going to need to find that length there. And we're told that the height of the frustum is 9 centimeters. So I'm going to do a couple of sketches here, one of the original pyramid and then a sketch of the pyramid that's been chopped off. So let's do that. Okay, so I've got two sketches there. This is the original pyramid and then this is the bit that's chopped off. So in terms of the original pyramid, we know that this length is 7.5 centimeters, so 7.5 centimeters, and we know that length is equal to 6 centimeters, but we don't actually know the height of it yet. And then in terms of the bit that's chopped off, we know that this part is 3 centimeters, so that would be, if we look at this rectangle, that'll be the same as that length there, so that's 3 centimeters there. So that's 3 centimeters there, and that's all we've got so far. Okay, so we've got our sketches, and now what I'm actually going to do is I'm actually just going to call the height of the shorter one h. Now what I'm going to do is I'm going to focus on this length here and this length here, because this is 3 centimeters and that's 7.5 centimeters. We know that the two pyramids are mathematically similar, because the pyramid that we started with, when we chopped the top of it off, that's going to be mathematically similar. The bigger one is an enlargement of that smaller one. So here we can find the scale factor of enlargement. So to find the scale factor of enlargement, we're going to do 7.5 divided by 3. So 7.5 divided by 3. And when we do 7.5 divided by 3, that's equal to 2.5, so 2.5. So that means the scale factor of enlargement between these two pyramids is 2.5. So if we know that 3 times 2.5 is 7.5, we can find this length here. And to find what this length here is, we can just divide 6 by 2.5. So let's get our calculator and do 6 divided by 2.5. And when we do 6 divided by 2.5, that's equal to 2.4. So that means that this length here is 2.4 centimeters. Okay, and that's just there, 2.4 centimeters. Okay, so this is fantastic. We now know that this length here is 2.4 centimeters. Now, but what would be really useful is if we could find the height of the pyramids, because if we can find the height of the two pyramids, we can find the volume of that pyramid, the volume of that pyramid, and take the volume of this smaller pyramid away from the volume of the larger pyramid, and that would give us the volume of the frustum. So let's consider the heights. Now, we let the height of the smaller one that's been chopped off be h. Now in terms of the height of the larger one, well, we know that's going to be 2.5 times larger. So if we take h and times it by 2.5, that's going to be 2.5 h. So we know that the height of the smaller one is h, the height of the larger one will be equal to 2.5 h. Now if we go back to the question, we had this diagram and we were given the height of the frustum. The height of the frustum is 9 centimeters. Now if you consider the height of the whole thing to be 2.5 h, and the smaller pyramid that is chopped off has a height of h, so that means if you take them away, so if you take this pyramid away, you're going to be left with the height of the frustum. So that means that 2.5 h, take away h, would be the height of the frustum. So 2.5 h minus h would be equal to 1.5 h. So that means the height of the frustum is 1.5 h. So we can make an equation that 1.5 h is equal to 9. So 1.5 h is equal to 9. And if you divide both sides of that equation by 1.5, we're going to get the h is equal to 6. So it means the height of the smaller pyramid will be 6 centimeters. The height that was chopped off is 6 centimeters. And if the height of the bit that's chopped off is 6 centimeters, and we know the height of the frustum is equal to 9 centimeters, 6 plus 9 is equal to 15. So that means the height of the whole pyramid that we started with would be 15 centimeters, so 15 centimeters. Or you could just take the 6 and times it by 2.5, and you also get that's equal to 15. So we know that's the height of the original pyramid. So this is fantastic. Now we can now find the volume of the original pyramid. We can find the volume of the smaller pyramid that was removed, and we'll take them away and we'll find the volume of the frustum. So let's do that. So for the large pyramid, the volume will be equal to 1/3 the area of the base times the perpendicular height. 1/3 the area of the base. So if we have a look at this larger pyramid, the base is a rectangle, the width is equal to 6 centimeters, the length is 7.5 centimeters. So if we do 7.5 times 6, that'll be the area of the base of that pyramid. So the area will be equal to 7.5 times 6. And 7.5 times 6, 7.5 times 6 is equal to 45 centimeters squared. So the area of the base of this pyramid is 45 centimeters squared. So let's go back down. So for this larger pyramid, this whole pyramid, we know that it's going to be 1/3 the area of the base, which is 45 multiplied by its perpendicular height, and we work that out to be 15, so times 15. So if we do a third of 45, which is 15, times that by 15, we get 225 centimeters cubed. So that's the volume of the larger pyramid. Okay, now let's find the volume of the pyramid that's removed. So if we go back up here and let's have a look at them. So this is the pyramid that's removed. We know that in terms of the base, it's got a length of 3 centimeters and a width of 2.4 centimeters, and the height of the pyramid is equal to 6 centimeters. So we've got enough information to find the volume of that pyramid. So let's do that. Okay, so in terms of the smaller pyramid, the volume would be a third the area of the base times the height. The area of the base, well, it was 3 centimeters by 2.4 centimeters. So if we do 3 times 2.4, that's equal to 7.2. So that's a third times 7.2 times the height of that smaller pyramid, which was 6. And if we work that out, we'll find the volume of that smaller pyramid. So we'll do a third times 7.2 times 6. And when we do that, we get an answer of 14.4, so 14.4 centimeters cubed. So this is fantastic. We now know the volume of the larger pyramid that we started with, which was 225. We know the volume of the pyramid that's been removed, which is 14.4. And if we take them away, that'll tell us the volume of the frustum. So 225 take away 14.4 is equal to 210.6 centimeters cubed. So 210.6 centimeters cubed. And that's it. Okay, let's have a look at our next question, question number 9. So question number 9 says, shown as the frustum of a cone. So we've got this frustum of a cone, so there would have been a larger cone, and then a smaller cone's been chopped off from the top of that larger cone, and what's left is the frustum. And we've been asked to find the volume of this frustum and to include suitable units. Now, one thing I noticed there is it says include suitable units, and we've got the height in millimeters, the diameter of this circle in millimeters, and then the diameter of the base in centimeters. I'm actually going to change the 1.1 centimeters into 11 millimeters, just so that they're all in millimeters. So that'll just help us whenever we're dealing with this question. Okay, the other thing I'm going to now do is I'm going to sketch the original cone and then the smaller cone that was chopped off. So let's do that now. Okay, so I've just sketched two cones. This cone's a bit wonky here, but this is the original larger cone, and then this is the smaller cone that's been chopped off. You can see the diameter at the base of the smaller cone is 8 millimeters, and the diameter at the base of the larger cone is 11 millimeters. In terms of the heights, we know the height of the frustum, but we weren't told any information about the height of the original cone or the height of the cone that was chopped off. So I'm just going to call that one h, because that's going to be the height of the smaller cone, and in a minute we'll find an expression for the height of the larger cone. Now what I'm going to do is I'm going to consider these two cones. These two cones are mathematically similar. The larger one is an enlargement of the smaller one. So here, to find the scale factor of enlargement, what I'm going to do is I'm going to divide the diameter of the base, that 11 millimeters, by the diameter of the base of the smaller cone, which is 8 millimeters, and that gives us a scale factor of enlargement. So 11 divided by 8 is equal to, and I'm just going to get my calculator, and do 11 divided by 8, and that's equal to 1.375. So that's the scale factor of enlargement. The scale factor of enlargement is 1.375. So that means that if the scale factor of enlargement is multiplied by 1.375, that means if the height of the smaller cone is h, to find the height of the larger cone, we times it by 1.375. So that'll be 1.375h. That's the height of the larger cone. So that's fantastic. Now, with these two cones, it'd be amazing if we could find the height of them. If we could find the height of them, we can find the volumes of them. And if we can get the volumes of them, we can take away the volumes to find the volume of the frustum. So let's find the height of these cones. Now, we do know the height of the smaller cone is h, and we know the height of the frustum is 6 millimeters. So it means that h plus 6, the height of the frustum, plus the height of the smaller cone, must be equal to the height of the larger cone. So h plus 6 is equal to 1.375h. So let's write that equation down, that h plus 6 is equal to 1.375h. And if we solve that equation, we can find h. So let's do that. So what I'm going to do is I'm going to take h away from both sides, or 1h away from both sides, so minus 1h and minus 1h. On the left hand side, we're taking away h to get rid of the h, we'd just be left with 6, so 6. And on the right hand side, we had 1.375h, we're taking away h, or 1h, so we're left with 0.375h. This is fantastic. So just going down a little bit here. I want to get rid of this multiply by 3.75. So let's divide both sides of the equation by 0.375 and divide by 0.375. And that'll tell us what h is. So 6 divided by 0.375 is equal to 16. So 16 is equal to h. So that means the height of the smaller cone is 16 millimeters. And in terms of the larger cone, well, we could do 16 plus 6 is equal to 22 millimeters, or we could do 1.375 times 16, and that's equal to 22 millimeters as well. So this is fantastic. We've now got two cones. We know the diameters of the bases of both of those cones. We've got the height of both of those cones, so we can find the volume of those cones. So let's work that out. So for the larger cone, the volume will be equal to a third pi r squared times the height. So it's going to be a third multiplied by pi multiplied by the radius of the base. Now the diameter of the base is 11 millimeters. So if we divide that by 2, we're going to get 5.5. So 5.5 millimeters squared. And then times by the perpendicular height of that larger cone, which was 22. So let's type this into our calculator and see what we get. And that's equal to 696.9099703 millimeters cubed. So that's the volume of the larger cone. Now let's consider the smaller cone. And again, its volume will be equal to a third pi r squared times h. So it's going to be a third multiplied by pi multiplied by the radius of the base. Now the diameter of the base of the smaller cone was 8 millimeters. So if we go back up here, the diameter of the base of the smaller cone was 8 millimeters. So that means the radius would be 4 millimeters. So it's going to be 4 squared multiplied by the height of the smaller cone, which was 16. And when we work that out, we get 268.0825731 millimeters cubed. So that's fantastic. We now know the volume of the larger cone. We've got the volume of the cone that was chopped off. So we subtract, we're going to get the volume of the frustum. So it's going to be 696.909 and so on. Subtract 268.08 and so on. And when we do that, we get an answer of 428.8273972 millimeters cubed. And I'm going to round that. I'm going to round it to 2 decimal places. So that'll be 428.83 millimeters cubed. And that's it. So that's the volume of that frustum. And that's it. Okay, let's have a look at our next question. Question number 10. So we're told, shown as a frustum of a cone. So we've got this frustum of a cone, and we've been asked to find the volume of the frustum. So we want to find the volume of that frustum. Now this question is a little bit different than the ones we've looked at so far, because the questions we've had so far, we've been dealing with the perpendicular height. The question has quite often given us the perpendicular height, but here we're actually told the slant height. The slant height of that original cone, so that diagonal length there, that slant height, is equal to 13 centimeters. So we may need to use Pythagoras' theorem here, because that'll be a right angle triangle with our 13 centimeters being the hypotenuse, 5 centimeters being one of the shorter sides, and the height, the perpendicular height of the original cone being the one of the other shorter sides. And then we can use Pythagoras' theorem to find the perpendicular height of that original cone. Okay, so let's start off by doing a little sketch. Okay, so I've done some sketches of cones. This larger one is the original cone. This smaller one is the smaller cone that's chopped off. Now I've noticed that the scales here aren't necessarily the best in my little sketches, because the radius of the smaller one is 4 centimeters and the radius of the larger one is 5 centimeters. Now if you have a look at my diagrams here, that looks a lot smaller compared to that 5 centimeters. I've put in the slant height of 13 centimeters there. And what we really want to do is we want to find the volume of the larger cone, we want to find the volume of the smaller cone, and then we want to take them away to find the volume of the frustum. So to find the volume of this larger cone, what we're going to need to do is we're going to need to use Pythagoras' theorem to find the height of the perpendicular height. So we've done this over sketch, this right angle triangle. We've got our 5 centimeters, that's the radius of the base. We've got this point here, that'll be the center of the base. We've got this point here, that's the top of the cone. And we've got the slant height here being 13 centimeters. So if we use Pythagoras' theorem, we can find h, the perpendicular height of that cone. And then if we find the perpendicular height of this cone, we can find its volume. Because remember, the volume of a cone is a third pi r squared times the perpendicular height. So then we can find the volume of that cone. Then we can find the scale factor of enlargement. So we can find what's the scale factor of enlargement, because this cone and the larger cone will be mathematically similar. So we can find the scale factor of enlargement, and we can then divide the perpendicular height by the scale factor of enlargement to find the height of this smaller cone, and then we can find the volume of it. So let's start off by using Pythagoras' theorem to find h, the perpendicular height of the larger original cone. So Pythagoras' theorem is a squared plus b squared equals c squared. A and b are the two shorter sides, so I'm going to call this a, this b, and the larger side the hypotenuse c. So a squared, that's going to be 5 squared, plus b squared, that's going to be h squared, equals c squared, that's going to be 13 squared. So we've substituted in our values, now we just need to work this out. 5 squared is 25, so we've got 25 plus h squared equals, and then 13 squared is 169. Now let's take away 25 from both sides of the equation, so we get that h squared equals 144, and then we can find h, the height of this triangle, by square rooting it to be then square root of 144 is 12, so 12 centimeters. So that means the height of this triangle is 12 centimeters. So that means the perpendicular height of this cone, let's just actually label it, the perpendicular height. So the perpendicular height of this cone is 12 centimeters. So that's fantastic. We knew the radius, we knew the slant height, and we used Pythagoras' theorem to find the perpendicular height. Now we find the perpendicular height of this cone, we can use the formula, the volume is equal to a third pi r squared h, to find the volume of that cone. In terms of this one, we know the radius, but what would be fantastic is if we knew the height, the perpendicular height of this smaller cone. So let's find it, because remember these two cones are mathematically similar, so let's find the scale factor of enlargement. So let's do 5 divided by 4, and 5 divided by 4 is equal to 1.25. So the scale factor of enlargement is times 1.25. So if we divide the perpendicular height, this 12, by 1.25, so let's divide by 1.25, we can find the height of this cone. So 12 divided by 1.25 is equal to 9.6, so 9.6 centimeters. So that's fantastic. So we've now got our two cones, we've got the length of the radius of the smaller one, the length of the radius of the larger one, the perpendicular height of both, and then we can use the formula, the volume is equal to a third pi r squared h, to find the volume of each of them. Then we can take away the volumes to find the volume of the frustum. So let's do that. Okay, so in terms of the larger cone, the volume is equal to a third pi r squared h. So it's going to be a third multiplied by pi, multiplied by the radius of the base, which is 5 squared, times the height, the perpendicular height, which is 12. And then if we work that out, we'll get its volume. And that's equal to 100 pi. So 100 pi, if you want to write it exactly, or as a decimal number, 314.159 and so on, centimeters cubed. So we've got the volume of the larger cone. Now let's consider the smaller cone. So again, its volume is a third pi r squared h. So it's going to be a third multiplied by pi, multiplied by the radius of the base, which for the smaller cone was 4 squared, multiplied by its perpendicular height, which is 9.6. And when we work that out, we get its volume. And that's equal to 160.849543.9 and so on centimeters cubed. So that's fantastic. We now know the volume of both the cones. Let's take them away to find the volume. So we're going to do 100 pi subtract 160.8495439, and that'll give us the volume of the frustum, which is equal to 153.309715. And we've not been asked to give it so many decimal places, so I'm going to choose 2, so it'll be 153.31 centimeters cubed. And that's it. Okay, let's have a look at the next question, question number 11. So question number 11 says, Lily is making a solid metal sculpture, and Lily has a solid metal cone with a base radius of 15 centimeters and perpendicular height of 24 centimeters. She removes a smaller cone from the top of the cone to leave a frustum. So this is a frustum that's left, and as you can see, there's that radius of 15 centimeters. It's got a height, the frustum, of 20 centimeters, and remember the whole cone to begin with was 24. So that means, I'm just going to get my ruler, that the extra bit that is removed, the cone that is removed, had a perpendicular height of 4 centimeters. Because that's the bit that's removed. So I'm just going to do a little sketch here. Okay, so that cone's removed. It's got a height of 4 centimeters, because obviously if the whole cone had a height of 24 centimeters and this frustum has got a height of 20 centimeters, that's the height of the cone that's removed. Then we're told the density of the metal is 5.8 grams per centimetre cubed. So every single centimetre cubed has got a mass of 5.8 grams. And the question says find the mass of the sculpture and to give your answer in kilograms. So first of all, let's find the volume of that frustum. If we find the volume of the frustum, then we can, if it's in centimetres cubed, times it by 5.8 to get its mass and then convert that into kilograms. So let's find the volume of that frustum. Now to find the volume of the frustum, well first of all what I want to do is I want to find the volume of the larger cone. And that's quite straightforward because we know the radius of the base is 15 centimetres and we know the perpendicular height of the cone is 24 centimetres. So that's going to be quite straightforward. In terms of the smaller cone, with that smaller cone we know the perpendicular height of the smaller cone, it's 4 centimetres, but we don't actually know the radius yet. So we're going to need to find the radius of that smaller cone. So we want to find that radius there, that distance there. So let's find the radius of that smaller cone. Now to find the radius of the smaller cone, remember it's mathematically similar to the larger cone, so if the larger cone is an enlargement of the smaller cone. And if the smaller cone has got a height of 4 centimetres and the larger cone has got a height of 24 centimetres, well what do you times 4 by to get to 24? So 24 divided by 4 is equal to 6. So it's 6 times larger. So the scale factor of enlargement is 6. So that means the radius of the base of the larger cone will be 6 times larger than the radius of the base of the smaller cone. So if we do 15 divided by 6, that'll give us this radius. So let's do that. So 15 divided by 6 is equal to 2.5. So that's going to be 2.5 centimetres. That's the radius of the smaller cone. So that's fantastic. We can now find the volume of the larger cone, find the volume of the smaller cone, subtract them, that'll be the volume of the frustum, and then get the mass of it. So let's find, that's 2.5 centimetres. Okay, so let's find the volume of the larger cone to begin with. So the volume of the larger cone will be a third pi r squared h, where r is the radius of the base and h is the perpendicular height. So it's going to be a third multiplied by pi, multiplied by the radius of the base, which is 15 squared, multiplied by the perpendicular height, which is 24. So let's work that out. And that's equal to 1,800 pi centimetres cubed. So that's the volume of the larger cone. You could write it if you want to as a decimal number, and as a decimal number it is equal to 5,654.866776, but I'm just going to leave it exactly as 1,800 pi. Okay, now let's do the smaller cone. So the volume of the smaller cone will be a third pi r squared times the perpendicular height. So it's going to be a third multiplied by pi, multiplied by the radius of the base of the smaller cone, which is 2.5 squared, multiplied by the perpendicular height of the smaller cone, which is 4. So let's work that out. And that's equal to 26.179938878 centimetres cubed. So that's fantastic. We now know the volume of the larger cone, 1,800 pi. We know the volume of the smaller cone, 26.17 and so on centimetres cubed. If we take them away, that's the volume of the frustum. So let's do that. And that's equal to 5,628.686838 and so on centimetres cubed. So that's the volume of the frustum. Now we know the density of the metal, and I remember we're told it's a solid metal cone, so that means it's a solid metal frustum. So that means if we want to find the mass of that solid metal frustum, we need to times its volume, 5,628.68 and so on, and it's on my calculator display, by 5.8, because that'll tell us the mass, because every single centimetre cubed has got a mass of 5.8. So if we multiply that by 5.8, that's equal to 32,646.38366 grams. Now that's in grams, we want it in kilograms, so let's divide by 1,000. So if we divide by 1,000, that's equal to 32.646 and so on kilograms. And the question didn't say to give it to so many decimal places, so I'm going to give it to, so 3 decimal places, the mass of that sculpture would be 32.646 kilograms, the 3 decimal places, and that's it. Okay, let's have a look at our next question, question number 12. So question number 12 says, the square base pyramid A is divided into pyramid A and frustum C. We've been asked to express the volume of frustum C as a fraction of the volume of the pyramid A. So in other words, what fraction of the volume of pyramid A is frustum C? And we've been asked to give our answer in its simplest form. Okay, now let's have a look at this. We have got this square base pyramid. We know that the length of the base is equal to 60 centimeters. So that means the width of the base is 60 centimeters, but we don't know any information about the height. So what we're actually going to do in this question is consider the fact that this pyramid here, this pyramid B, is mathematically similar to pyramid A. So these two pyramids are mathematically similar. In other words, pyramid A is an enlargement of pyramid B. And if we have a look here, we know for pyramid B, the side length of the base, so this square has got a length of 15 centimeters, and we know the side length of the base of pyramid A, so we can find the scale factor of enlargement. The scale factor of enlargement will be 4. Pyramid A is 4 times larger than pyramid B in terms of its lengths. Now let's consider that. So let's think back to similar shapes. Now if we know the scale factor for the lengths is n, then for the areas it'll be n squared, and for the volumes it'll be n cubed. So if, for instance, we had a rectangle and the larger one, the side length was 2 times larger, the area would be 4 times larger because 2 squared is 4. So the area of the larger rectangle will be 4 times larger than the smaller one. If you had a cube and the sides were 3 times bigger, the volume of the larger cube would be 27 times bigger because you would cube that 3, and that would give you the scale factor for the volume. So in this case, we know the sides are 4 times larger. If we wanted to compare the surface area, that would be 4 squared is 16 times larger. And for the volume, we'd do 4 cubed, which is 64 times larger. So that means that here, the volume of this pyramid is 64 times larger than the volume of this pyramid, because we know the scale factor for the sides is 4, so for the volume it's 64. So that means the volume of this pyramid is 64 times the volume of this pyramid. So that means that this pyramid, the volume of it is 1/64th the volume of that one. If you wanted to find the volume of this pyramid, you would divide the volume of this one by 64. So let's write that down. So I've just written down the volume of B is 1/64th the volume of A. So in other words, the volume of that pyramid is 1/64th the volume of this one. Now this volume and this volume must add together to be that volume. So if we take that volume away from this volume, we'll be left with the volume of the frustum. So let's do that. So I'm going to let the volume of A be 1, the volume of that original pyramid. I'm going to take away the volume of B, which is 1/64th that volume. And then if we do 1, take away 1/64th, we're left with 63/64ths. So that means that the volume of C, the volume of this frustum, so that means the volume of C, the frustum, would be 63/64ths the volume of that pyramid. And you could test that. If, for instance, you let the height of this pyramid be 8, and then that means the height of this one will be 2, because obviously the lengths are 4 times smaller for B than for A, then you can find the volume of that, you can find the volume of that, take it away, find the volume of C, that frustum, and then see if that volume is 63/64ths the volume of the original one. And that's it. So the question asks us to write down the volume of frustum C as a fraction of the volume of pyramid A. The answer would be 63/64ths. Okay, let's look at our next question, question number 13. So question number 13 says a frustum is formed by removing a small cone from a larger cone. And here we've got the frustum. So in terms of the circle at the bottom of the frustum, that base, we know that its radius is 14 centimeters. And in terms of the circle at the top of the frustum, we know its radius is 7 centimeters. And the question says the volume of the frustum is 9,000 centimeters cubed. And we've been asked to work out h, the height of the frustum. Okay, so in terms of this question, it's a little bit different than the ones we've looked at so far, because rather than being asked to find the volume of the frustum, we want to find h, the height of the frustum, but we know its volume. Now, if we want to find the volume of that frustum, what we would typically do is find the volume of the bigger cone, find the volume of the smaller cone that's been removed, and take them away. So that's actually what I'm going to do. I'm going to find the volume of the smaller cone, the larger cone, and then take them away, and then put that equal to 9,000. Now, before we do that, one thing I want to notice here is the height of the frustum. The height of the frustum is h. Now, if we have a look at this frustum and we consider these radii, if we actually have a look at the larger cone, the radius of its base is 14 centimeters, and the smaller cone, the radius of its base is 7 centimeters. So that means the scale factor of enlargement will be 2. So that means that the height of the smaller cone, if it was h, the height of the smaller cone is equal to h, that would be really good, because that means that if the height of the smaller cone is h, the height of the larger cone would be 2h, which is twice as big. So that's fantastic. So we now know the radii, we know the heights of the two cones, so we can find expressions for their volumes. So let's do that. And just remember the volume of a cone is equal to 1/3 pi r squared h. So what we're going to do is we're going to substitute the radii and we're going to substitute the heights. So let's do that. So in terms of the larger cone, for the larger cone, we've got its volume will be equal to 1/3 multiplied by pi, multiplied by its radius, which is 14 squared, multiplied by its height, which would be 2h, because obviously the height of the larger cone would be 2h. And let's work this out. So if we work out a third times pi times 14 squared times 2, and then we can just put the h after it, that'll be equal to 392 over 3 pi h, or as a decimal number, if we wrote it as a decimal, that'd be equal to 410.5014401 h. So that's the volume of the larger cone in terms of h. In terms of the smaller cone, the volume of it would be a third, multiplied by pi, multiplied by its radius of its base, which is 7, so 7 squared, multiplied by its height, which is just h. And when we work that out, we get that's equal to 49 over 3 pi, then h, or as a decimal number, it's equal to 51.3126801 centimeters cubed. So that's fantastic. We've now found an expression for the volume of the larger cone in terms of h, and we've found an expression for the volume of the smaller cone in terms of h. And if we take them away, that'll be the volume of the frustum. So let's do 410.5014401 h, subtract 51.312 and so on h, and see what we get. So that'll be equal to 359.1887601 h. So that's the volume of the frustum. But the question, we were told the volume of the frustum, is 9,000 centimeters cubed. So that means this is equal to 9,000, 359.1887601 h equals 9,000. And then if you divide both sides by 359 point so on, you get the h is equal to 25.056463334. And that's it. So that's the height of the frustum, that's h. So our answer is 25.056 to 3 decimal places. And that's it. Okay, let's have a look at our last question, question number 14. So question number 14 says, Anna made a solid conical ornament. So this is a solid conical ornament. And the top of the ornament A is made from aluminium, and the bottom of the ornament is made from zinc. So this is solid aluminium and this is solid zinc. So we've got this cone at the top and this frustum beneath. The density of the aluminium is 2.7 grams per centimeter cubed. So every single centimeter cubed of that cone has a mass of 2.7 grams. And the density of the zinc is 7.1 grams per centimeter cubed. So every single centimeter cubed of this frustum has a mass of 7.1 grams. And we've been asked to find the mass of the sculpture and to include suitable units. So what we're going to need to do here is we're going to need to work out the volume of the cone, we're going to need to work out the volume of the frustum, and then what we're going to do is we're going to find the mass of those by using the density. Okay, so let's start off with the volume of the cone. If I wanted to find the volume of this cone A, what I would do is I would use the formula, a third pi r squared h. So we need to find the perpendicular height of A. So actually, if we have a look here, we've been given the slant height of the whole cone. We've got the radius of the base of the whole cone. Let's find the height of the whole cone to begin with. So let's find this whole height. So the height, let's call it h. So the height h. We're going to use Pythagoras' theorem. So Pythagoras' theorem is a squared plus b squared equals c squared. I'm just going to move the camera there. So a squared plus b squared equals c squared. So a squared will be 20 squared. B squared, we're going to call that h. And c squared is the hypotenuse, the longest side, so that's 52. So a squared, that's 20 squared, plus b squared, that's h squared, is equal to c squared, so that's 52 squared. So let's work this out. 20 squared is 400 plus h squared is equal to, and let's work out what 52 squared is. 52 squared is equal to 2,704. So that means the h squared would be equal to, if we take 400 away from both sides, 2,304. And then if we square root that, we're going to get an answer of 48. So h is equal to 48. So that means the height of the whole cone is 48 centimeters. Now, one thing I've noticed here is we've got our smaller cone and our larger cone. Remember, they are mathematically similar. The bigger one's an enlargement of the smaller one. So the scale factor of enlargement, to go from 5 to 20, we would times by 4. So that means the scale factor of enlargement is 4. So if the height of the whole cone is 48 centimeters, if we divide that by 4, 48 divided by 4 is equal to 12. So it means the height of this smaller cone A is 12 centimeters. So that's fantastic. We now find the volume of that smaller cone. We can find the volume of the bigger cone as well. And if we take the volume of the smaller cone away from the volume of the bigger cone, we'll get the volume of the frustum, and then we can work out the mass of both of those. So let's start off with the volume of the bigger cone. So the volume will be equal to 1/3 multiplied by pi, multiplied by the radius of the bigger cone, which is 20 squared, and then multiplied by the height of the bigger cone, which is 48. And when we do that, we get an answer of 6,400 pi centimeters cubed. So that's the volume of the bigger cone. Now let's find the volume of the smaller cone. So that's 1/3 multiplied by pi, multiplied by the radius of the base, which is 5 squared, multiplied by its height, which is 12. And when we do that, we get a volume of, that's equal to 100 pi. So 100 pi centimeters cubed. So that means the volume of this smaller cone A would be 100 pi centimeters cubed. We've got the volume of the bigger cone, so if we take the volume of the smaller cone, the 100 pi, away from the 6,400 pi, we'll get the volume of the frustum. So let's do that. So the volume of the frustum will be equal to 6,400 pi, subtract 100 pi, would be equal to 6,300 pi centimeters cubed. Now in this question I have worked exactly, I've worked in terms of pi just because they were quite nice numbers. So we've got the volume of the smaller cone, we've got the volume of the frustum, now we can work out the mass of both of those. So let's start off with the smaller cone at the top. The smaller cone has got a volume of 100 pi. So the smaller cone has got a volume of 100 pi, and then that would be 314.159 and so on centimeters cubed. And each one of those centimeters cubed has got a mass of 2.7 grams. So if we take the 314.159 and so on and multiply that by 2.7, that'll give us the mass of the aluminium section of this ornament at the top. So multiplied by 2.7 is equal to 270 pi, or 848.23 and so on grams. So that's the mass of the cone at the top, the aluminium part of the cone. Now, if we want to work out the mass of the frustum part of the ornament, which is made from zinc, we're going to take its volume, which is 6,300 pi, or as a decimal number, 19,792.03 and so on. We're going to multiply that. Each one of those centimeters cubed has got a mass of 7.1 grams. So if we times it by 7.1, that'll give us the mass of the frustum part of the ornament. So we're going to multiply by 7.1, and that's equal to 140,523.439 and so on grams. So that's fantastic. We now know the mass of the aluminium part of the ornament, so the top of the cone at the top. We know the mass of the zinc part of the ornament, the frustum beneath. We've been asked to find the total mass of the sculpture, so let's add them together, and that'll give us the total mass. So let's do that. So 848.23 and so on, plus 140,523.439 and so on. If we add them together, what do we get? That's equal to 141,371.67 grams to 2 decimal places. Now we've been asked to give it in suitable units. I'm going to change this into kilograms. I'm going to divide it by 1,000. And that gives us an answer of 141.37 kilograms to 2 decimal places. And that's it, that's the mass of the sculpture. And that's it. So these have been the video solutions to the Corbettmaths Practice Questions on the volume of a frustum. I really hope you found this video useful, and if you have found it useful, please like it and please subscribe to the YouTube channel. Thank you, cheers, bye.